We're going to be talking about unstressed vibration analysis today. We're going to talk about why it's important, how it can be run. We're going to have a demonstration from Andreas as well, how we can interpret the results, and look at some tips and tricks as well. So let's just jump right into it now. Why do we want to run a vibration analysis? And this is a pretty loaded question, but I've tried to lay it out in a few different points here. So I think the most important aspect is that we want to run some sort of dynamic analysis beyond just understanding our mode shapes and so on. Understanding the dynamic characteristics of your model is a really good first step. And when I say dynamic characteristics, I mean things like the mode shapes, the natural frequencies, period of vibration, and so on, mass participation. This is all very important information if you want to run a time history analysis, a response spectrum analysis, for seismic loads or some sort of other type of time varying load that might occur. And another aspect of this is that you can run vibration analysis, specifically unstressed vibration analysis, early on in your modeling process before you've even applied your loads. So it helps you spot modeling errors perhaps that could occur while you're still fairly early and in the malleable stages of your modeling process. And we'll look at, in the next couple of slides, some examples of where that can be spotted. So I'm just briefly going to touch on how we can run a vibration analysis. Andreas is actually going to be doing a demonstration on this as well, so he'll be going into a little bit more detail than myself. But there are a few points to think about when we set up the model. First of all, the fact of the matter is that the dynamic characteristics that I mentioned earlier, the natural frequencies, the mode shapes, and so on, are very dependent on the stiffness and the mass of our model. So it's good to put some thought into how those are represented. And obviously stiffness is perhaps a little bit more directly modeled with the potentially use of springs and boundary conditions or the material and section properties of your model. But you do actually have some flexibility in how you can model the mass as well. And this can be an important aspect to either simplifying your model or just representing it in a more accurate way. So we have ways of using lump mass. And this is pretty common for building models, for example, where you might have a multi-story structure where the mass is predominantly lumped at the floor locations. So some people will even simplify this to a stick model like you see on the right-hand side and say, well, I know the weight of my floors. They're in the lateral direction. I'm going to have some mass when I'm looking at lateral analysis. And I'm going to lump my masses at that location. We can also have system mass. So every element we have a material applied to that, and that material will have its own force density. And that can go into basically determining the system mass for the structure at various locations, not lumped at specific locations, but more distributed throughout the entire structure. And of course, if we have significant chunks of mass that are not structural and are not modeled into our structure, but could represent a load, for example, snow sitting on top of a structure, we may want to also look at the effects of that load being converted to a mass, which could have a significant effect on the model. As we mentioned, the characteristics of our model are fairly dependent on stiffness and mass. And the last point I want to touch on in this slide here is element subdivision. So we have, obviously, when we're looking at the previous slide and we're looking at different mode shapes, there's a variety of different mode shapes that can be represented. Some of them are, like some of the lower modes may not necessarily require as many elements to represent the oscillations and so on. But as we get into higher modes, we might have some sort of sine wave shapes within our columns or our beams or even our slabs, for example. And to really represent that accurately, we would want to make sure that we have a large or more elements. And so subdividing our elements can certainly go a long ways in terms of characterizing those types of mode shapes. We also have the question of, do we want to run an unstressed or a stress vibration analysis? And the question I always ask here is, well, is the stress state of your model going to be significant? And it's somewhat hard to quantify. But what this analysis allows you to do is it allows you to consider P delta and nonlinear effects when calculating the mode shapes. So an example of this might be if you have a large compressive load on your structure, the structure may be close to its buckling limit. And at that limit, the vibration characteristics or the dynamic characteristics are going to be different than if it were pulled into tension, for example. Think of a guitar string. If you pull it into tension, it's going to oscillate at a higher frequency than if it were not tensioned at all. Another aspect is to ensure that the number of eigenvalues requested are going to be able to capture the mass participation in your model. And this is something that, again, requires a bit of knowledge of the model, the number of degrees of freedom that you have, and obviously the mass participation. So it might require some investigation to get that right. But that just ensures that you're getting a truly accurate capture of the overall response of the model, or the dynamic characteristics, rather. So after we've run the analysis, we have to think about how are we interpreting these results and what sort of results are we getting out of the model? Well, there's a few different bits of results that we get out of this. We get natural periods and frequencies, which you've heard already. So we get the dominant frequencies, which will have the most mass participation. And we have perhaps unexpected results as well. So in this example right here, we can see an example where we've got a two-story frame with a slab on top, and for the most part, all of the structure is kind of oscillating in the same direction. But here we notice that there's a column that didn't go along for the ride. And this may be difficult to spot within the building of the model because everything is nice and plumb. We're not having any deflection. So we're kind of expecting it to look like it would be pointing straight up as it is currently rendered. But now when we're running this vibration analysis, even if we haven't applied any loads, we can see here that all these columns and the slab are moving to the left during the mode shape, except for this one here. It doesn't seem to be attached to the slab above. So this is a great way to spot these types of potential modeling errors earlier on in the process when perhaps it's a little bit easier to make those modifications. Now we'll look into more of the results later on and describe those in more detail. And just a few tips and tricks as well. We talked about element subdivision, and Andreas is going to go into an example shortly on how this can make a difference in your results. Effectively, you have to think about, in this example, where we've got a mode shape that's represented with two variations of the same model. So these members in between these joints have the same stiffness, the same mass exists within the same model. But the difference here is that we're getting different mode shapes because we're using essentially different pieces to put together that mode shape. As you can see in the top model, we're just discretizing this member with two different segments. So to represent a sine wave, it's going to be a little bit faceted, but we're getting a much better curve representation in the model below. And this can be accentuated in other examples as well. Some other ways that we can verify this information, we can run a free vibration analysis with time history analysis to compare the results. So if we're unsure of how we're getting this information, we can run an analysis. So an example of this would be applying an initial displacement or velocity to a joint in our model, almost like if you're holding a ruler and you just in one hand and you push it over with your finger to one end and let it go, it's going to oscillate with its natural frequency. That can be effectively emulated with time history analysis. SView is also a great tool to study mode shapes, and we'll see some examples of that. And we have options for the different eigenvalue extraction methods as well. We might not be going into too much detail on this in this presentation, but there are some suggestions for using Jacobi if you have perhaps a single degree of freedom system or not very many degrees of freedom and you want to calculate all of them, versus subspace iteration can be more efficient for larger models, but doesn't necessarily, or it won't calculate all the mode shapes for you. It's just going to do the lower half. So we're going to jump into the demo now. So Andres, I'm just going to transfer you the control if you don't mind taking over from here.
Sure thing. Thank you very much, Matt. All right. Can you see my screen now?
Yes, thank you.
All right. So, well, thank you very much, Matt. First of all, hello, everyone. My name is Andres, and I'll be glad to be giving you a very brief demo to better illustrate the vibration analysis that we have just discussed. So what we have here is a simple frame. Even though it's a 2D frame, as you can see, we can see that we're actually working in 3D mode. So let me just go back to the front view. And with that said, what we have is a total of 6 degrees of freedom for each one of these joints over here, except for the supports that are fully fixed, as you can see. So those degrees of freedom would be translation about the X, Y, and Z axis, and rotation about the X, Y, and Z axis as well. This for each one of these joints. So I'll just be moving very quickly to running the analysis now. Let me drag this window over here. Oh. And what we can see here is what Matt just explained to us about the two different methods to extract the eigenvalues, which are the subspace iteration method and the Jacobi threshold method. We can use any of them, but I'll be shooting for the Jacobi threshold method. And as this one is indeed a small model, and the reason why we explain the number of degrees of freedom for each joint is that I have to input a number of total eigenvalues over here. This number has to be an accurate number, and the Jacobi method will extract all of the eigenvalues, and the subspace iteration method requires twice as many to exist as can be extracted. So how does this translate to plain English? If I input a number here that is more than half the available degrees of freedom, in this case, we would trigger an error message and the unstressed vibration analysis will not be executed. So this is an important factor to keep in mind. I'll just input 6 eigenvalues for this model, and I will run the analysis. Once the screen results get to our screen, this happened on my first monitor, so if you didn't see that, I can go to the mode shape tool here in the graphical result window, and we can start reviewing the different mode shapes for our structure. So a mode shape is a deflection pattern related to a particular natural frequency, and it represents the relative displacement of all the parts of the structure. Usually, we're mostly interested in the ones that have a major participation of mass in the different axes, which in this case would be X and Z, as we're looking at a model in 2D. And it's not uncommon for mode shape 1 to be the one with the biggest mass participation in X, as you can see here. And well, at least for small models like this one. So an almost 100% participation for X in this case is a good indicative that this is indeed the mode shape of interest for our design. So let me just run an animation on this. I hope that you can see it clearly. We are better visualizing the dynamic behavior of this structure with this animation, and I can switch between the mode shapes and run the animations to see the different eigenvalues that I have just defined in my previous step. So let me just go back to the first one. As we mentioned, one of the most important aspects of the results is the structure's period. This period represents the time it will take the structure to complete an oscillation, as we just mentioned, and in this case, it's 0.1561 seconds, as we can see here, which is a very small period. So what does a small period mean? A smaller period means that the structure is oscillating faster, and it means that the frame is also stiffer. All these results can also be shown in a condensed way in S-Frame through the numerical results window over here. Once again, we can see the results for all the eigenvalues that I defined, that there were 6. And we can see more information here. We can see the structure's frequency, which is very important for our applications. We can see the angular frequency, the participation percentage, and the mass participation factor in each direction. And let's just keep these results in mind, as they will be a good comparison point when we have executed a similar procedure on our second example. So let me just jump real quickly into my second model over here. So this is our second model. As you can see, it's then again a fairly simple 2D frame again. It's fully fixed, but this time we have subdivided the 3 members 3 times each one. So what does that mean? As mentioned before, we will be expecting more accurate results when we have more members defined. Having added more members to this frame, we now naturally have more joints too, as you can see. So if I click on the Run Analysis button once again, let me just bring this guy here, put it here so we can visualize our structures at the same time. Because now we have a total of 8 free joints over here, 1, 2, 3, 4, 5, 6, 7, and 8. This means that each one of these joints can move in the 6 degrees of freedom each. So that would equal 48. And as I cannot exceed half of the possible directions of movement for the whole model, my total eigenvalues this time are now going to be set to 24. But I could have also ran a non-stress vibration analysis with the same 6 total eigenvalues as we did before, and the results wouldn't change for the different number of eigenvalues, as the dominating mode shapes are still going to be the first ones. But I've already run an analysis on this one, so I'm just going to click on cancel here. Let's jump straight into the graphical results. So we can notice that we have a major participation of mass in the X direction for mode shape 1. Oh, sorry. This is showing mode shape 9. Let me just go back to mode shape 1. There you go. And this time, the structure's period has increased by very little. It's now 0.1564 seconds. And to complete, it's going to take that time to complete the oscillation, sorry. And as we now have a better mass distribution, having more members and joints, this mass participation has dropped down to 85% for the X direction. But it's still clear that this mode shape is dominating, and it will be the one that we are mostly interested in. So I'm just going to run an animation over here again. And if you're attentive to small details, in this case, you will see that these two columns are deflecting in a slightly more realistic way than the first time around, in which they were slightly more straight, so to speak. And if I actually scroll through the different mode shapes, as you can see right here, I will now see these more interesting deformed shapes than the ones that we saw the first time around. Then again, these shapes are more like real case scenarios, having added more joints to our frame. But don't be scared. This is just an exaggeration of the real structure's behavior. So why don't we go to compare the results for our two models? So now that we have run the two analyses in our analog models, we can start comparing the results. Above, you can see the results for the first analysis, and below, we can see the results for the second analysis. As you can see, I have my 24 eigenvalues over here. So as we mentioned before, the periods for the second model increased by just a little bit, and the mass percentage of participation has also decreased for the second example over here. And we will still have a very clear dominant mode shape, so this is positive results. And for each direction in both cases, nevertheless, for these will be the ones that we'll be using to design our structure, meaning the mode shape 1 in both cases. And the building's frequency for each mode shape has decreased as the period increased, and our participation factors, have also spiked up for the second model over here, at least for the X direction, and we can see a slightly smaller participation factors in the Z direction for the second model as well. So let me just jump real quickly to this slide, and just to give a little bit more context to what we have just shown with the numerical results, we have this graph over here that shows us how increasing the number of elements will allow us to find the convergence of results for the building's natural frequency and reach the one true solution that will help us moving forward. Let's not forget that the building's natural frequency is an important value for structural engineering, as we will try that this frequency never matches the frequency of the seismic waves at the desired location, which would be inevitably causing the structure's failure. So with this quick demo, we hope to have been able to prove the point of modeling more realistic structures to reach more accurate results to design safer structures during dynamic loading scenarios. Thank you very much for your attention, and back to you, Matt.
Thank you, Andres. Let me just take back the control here. Okay, so I guess if we can wrap this up here, just a few, I guess, objectives that we had for this type of webinar, coffee break series, if you will. We wanted to perhaps demystify this type of analysis. I know some of you in attendance are already using SJM for this type of analysis, and that's great to see. But as we visit clients, we do find that there's perhaps less experience in this for some of our users in this field. And I don't think there is necessarily as big of a technical hurdle to climb as some people may think or speculate. So we wanted to make sure that you knew that this isn't something that requires you to, it's not rocket science, I guess you could say. It does go a long way to understand the dynamic behavior. If you understand your dynamic behavior, especially if you're going to be running further dynamic analysis, you're going to have a good kind of footing to build off of. But as we mentioned already with spotting modeling errors and so on, it can be useful to understand if the model is behaving the way you expect it to without the presence of loads. It can be a good tool to spot that. All right, and with that, I'd like to thank everyone for their time, and we hope to see you guys all in the next presentation on response spectrum analysis.